All right, let's get right into it. When we first learn about electricity, we usually think about just two charges. Nice and simple, right? One pushes, one pulls. But let's be real, the universe is way more crowded than that. It's like a giant chaotic party full of charges. So what happens then? So yeah, that is the big question, isn't it? Picture yourself as a single charge, and you've got all these other charges buzzing around you. Some are pushing you away, others are pulling you in. How in the world do you figure out the total, the net force that you're actually feeling? It sounds like it's going to be a huge mess, but the answer, well, it's actually incredibly elegant. Okay, so before we can crash that chaotic party, we got to take a step back. We need to revisit the most basic rule of the game, the one that governs how any two charges interact, just one-on-one. And that rule is, of course, Coulomb's law. This is our foundation. It's the bedrock principle that tells us exactly how strong that push or pull is between any single pair of charges. Here it is, the formula we all know. It just says the force depends on how big the charges are, and crucially, the square of the distance between them. It's all very predictable. This force, F12, is just about the relationship between Q1 and Q2. But what happens when a third one shows up? All right, now things get interesting. We're introducing a new player to the game, a third charge. And this is where you think things might get really complicated. And just look at this diagram. It lays out the new problem perfectly. We've still got that original force, F12, acting between our first two charges. But now, this new charge, Q3, is exerting its own force on Q1, a force we're calling F13. So suddenly, our poor Q1 is feeling two different forces at the exact same time. And this all boils down to one really critical question. Does this newcomer, this Q3, somehow mess with the original force between Q1 and Q2? Do they start pushing or pulling on each other differently just because there's a third wheel watching them? Well, the answer to that question is a big, resounding no. And it's all thanks to one of the most beautiful and powerful ideas in all of physics, the superposition principle. This is it. This is the absolute key. It turns out that electric forces just don't care about each other. The force between Q1 and Q2 behaves as if Q3, Q4, and a million other charges don't even exist. Each pairwise interaction is its own private conversation. So here's the formal rule. To get the total force on any one charge, you just calculate the force from every other charge individually, one at a time, and then you just add them all up. But here's the crucial part. You have to add them as vectors. The direction of each push and pull matters a lot. And what's so amazing about this is it gives us a super clear step-by-step playbook. It turns a really complex problem into a bunch of simple little ones. First, you figure out the force from Q2, pretending nothing else is there. Then, you do the same thing for Q3. Then, you just add those two arrows together to get your final answer. Easy. And when you write it out mathematically, it's just this beautiful and simple. The total force, F1, is just the force from charge 2 plus the force from charge 3. That's it. A messy situation solved with simple addition. Okay, but here's where it gets really powerful. This whole principle isn't just a neat trick for three charges. No, it scales up perfectly no matter how ridiculously crowded that party gets. And this diagram just shows it all. I mean, look at that. It doesn't matter if you have 5 charges or 10 or a billion. The total force on that one charge in the middle is just what you get when you add up all those individual force vectors, one by one by one. So this is the grand finale, the ultimate expression of the rule. For n charges, the total force is just a big long sum. The force from charge 2, plus the force from charge 3, plus 4, and so on, all the way to the last one. It's a completely linear, additive world, which makes the physics surprisingly manageable. So, you might be thinking, what's the big deal? Why does this one little rule matter so much? Well, because this isn't just some handy trick for solving homework problems. It's one of the absolute pillars of how we understand our universe. I want you to just let that sink in for a second. That is a huge statement. It means the entire field of electrostatics, how charges sit still and create fields and store energy, the whole shebang, it's all built on just two simple ideas. Coulomb's law for a pair of charges, and the fact that you can just add up all their effects. That's it. And that leaves us with this really awesome thought to chew on. Nature took something as incredibly complex and fundamental as electromagnetism and built it on a foundation of simple addition. It just makes you wonder, right? What other huge, chaotic looking systems out there are just governed by their own beautifully simple underlying rules that we just haven't found yet?